Good afternoon, everyone. In this morning, I show you the application of 3D angle gathers in velocity model building. So in this talk, I will introduce more details about the construction of the 3D angle gathers using wave equation to extend the images. So here is the same image you have seen this morning. So this is the migrated image of the wave field. So the migrated image here is actually a characterization of the reflectivity of the subsurface as a function of space x, y, z, as you have seen in the picture. But in most cases, we also want to characterize the subsurface reflectivity as a function of angle, for example, reflection angle or azimuth angle. So here is an example of the gathers. So here, what I show here is the gathers which characterize the reflectivity for all reflection angle and all azimuth angle. So you can see in the bottom two panels, the reflection angle theta goes from minus 90 to plus 90, and on the top panel, the azimuth angle goes from 0 degree to 360 degree. So the unfolded cube you see on the left actually correspond to three spatial slices of the cylinder on the right. So the bottom two panels corresponding to the blue and right slides of the cylinder, and the top panel corresponding to the green slides of the cylinder. So 3D angle gathers has a lot of application in the imaging project. So we are interested to see how we can construct these gathers in the wave equation migration. So there are two different kinds of methods we can use to get angle gathers during the migration. So the first category of the method, we decompose the wave fields into angle gathers by using either the Poynting vector or local Fourier transform, or we can also decompose the images, particularly the extended images, into the angle gathers. Natalie will actually show you a comparison between the angle decomposition method using Poynting vector and extended images. So in this talk, I will focus only on the methods based on the extended images. Actually, there are also two different methods we can use to decompose the extended images into angle gathers. So first one is using common image gathers. In particular, the extended images with space lag extension shown on the top, and also we can use common image point gathers, which is the extended images with lambda and tau extension shown on the bottom. Here I use red color C to emphasize the fact that the common image point gathers are constructed on individual points on the reflector, so the gathers are actually localized on the reflector. So to highlight this difference between these two gathers, I plot a cartoon. So in this cartoon, the top surface corresponding, the top panel corresponding to the surface. So there's a blue star represent the source, and the bottom panel corresponding to the reflector plane. So you see that for CIG, we construct the gathers as for all depth levels. So the gathers we obtain is a function of depth. But for CIP, we only construct the gathers locally, which is a point on the reflector. So the gather you obtain is actually a function of legs, the space legs and the time lag. But for these two gathers, the way they characterize the reflection is actually similar, as the example shown here. So on the left, I show you the gathers construct for one interface, one reflector model, and you can see that the gathers, the CIG characterize the reflection in z, lambda x, and lambda y space. But for CIPs, the gathers characterize the reflection in tau, lambda x, and lambda y plane. lambda white space. But in both cases, you can see the kinematics of the reflection indicators are similar. And actually, what we obtain in the indicators is a plane, and the slope and the orientation of this plane depends on the reflection and azimuth angle. So this provides the basis for the angle decomposition algorithm. So basically, what we do is we associated the kinematics of the reflection plane in the indicators to the reflection and azimuth angles. And this is done by deriving a geometric relationship describing such kinematics in the indicators. So here I show you the move out function we use to decompose the indicators into angle indicators for both CIGs and CIP. So you can see at least the reference for both methods. So if you want to know more mathematical details regarding the derivation, you can refer to the paper there. But essentially, for CIGs, we characterize a reflection angle theta and azimuth angle phi in the vector q. So the vector q is actually the vector lies between your reflective plane and the reflector. So this vector contains the azimuth information. And for CIG formula, the Z0 represents the image point at zero lag, and the NZ is simply the vertical component of the normal reflection normal. So we need to estimate the dip first before we can decompose the data to get the angle information. And for CIP, the formula is also describe the geometric relationship. And in this case, we describe the relationship between tau and time lag tau and the space lag lambda. So we there represent the local migration velocity. Notice that in both cases, in both formula, we use n dot lambda equals 0. So this formula actually indicate that only the space lag orthogonal to the reflection normal contribute to the angle decomposition. So although the formula for CIG is developed in 2010 from my first paper, but I just realized that I can implement this to construct the 3D angle getter recently. So in the following talk, I will focus on the application of CIG only. So here is a simple example to illustrate the angle decomposition based on CIGs. So this is the migrated image of a one-layer model. So now I will show you three different CIGs and the corresponding angle decomposition. And to convince you that the formula I just introduced can capture the angle information accurately. So the first example I use is I put the getters right below the source. So again, the blue represents source and the red represents the getters. So in this case, the reflection plane in the getters is horizontal. And if we apply the angle decomposition, we get the event in 0 deflection angle. And in this case, we have no azimuth information. And next, but I forgot to mention the box on the right just show the geometry of the getter and the source. So next is another getter construct at a different location, and you see in this case we have a change in the kinematics of the event in the getters, and because of this change, when we apply the angle decomposition, the algorithm capture the event at different azimuths and reflection angle. So the convention here we choose is that we use the getter location as the reference. So imagine that if we stand at the location of the getter, then we will see the shots coming from our north direction. So that's why you see the event in 90-degree azimuths. And the final example is another. I choose another location for the getter. In this case, you can see both the slope and orientation of the reflection plane indicators are different. And therefore, the angle decomposition algorithm also capture this change and correctly put the event at the corresponding reflection and azimuth angle. So I hope this simple example demonstrates that our formula is valid to capture the angle information from the extended images. So now let's go back to the field data example I showed you before. So this is the image you saw before. Before I show you the gathers, I would like to show you the acquisition geometry we use to get this image, so that we can compare whether the angle gathers we obtain is consistent with the geometry for this data set. So this data set is actually an OBC data set. So when we do migration, what we do is actually we migrate the common receiver gathers represented by the blue star there, and again the red dot represent the gather location. So you can see in this case we have more shots, we have more receiver cover in the inline direction and less receiver along the cross-line direction. So in this case the receiver is equivalent to the source. So this is the space lag extended images we construct using the acquisition geometry at the middle of the model. So you see now we have more events and much more complicated reflection kinematics. And now let's see whether our algorithm can still capture the angle information from the gathers. And again, this is the final angle gathers you have seen before. So notice that in this case, if you look at the top panel, we observe that the distribution of the events actually is mainly on the inline direction rather than the cross-line direction. And the bottom panel is simply the reflection angle panel at two special azimuths, 0 and 90. But from this angle decomposition result, you see that our algorithm captured the information for all reflection and all azimuth angle from the extended images. So to summarize, I introduced to you the angle decomposition methods based on wave equation extended images. Especially in this case, we can see that the formulation for the angle decomposition using CIPs and CIGs are similar. And the angle gathers has a lot of application in the imaging project. For example, QC the velocity model building, and also they can be used to design the acquisition geometry. So with this, I would like to thank Dr. Oil and Warby License Partners for providing the data, and thank you for your attention.